In this video, I want to introduce the idea of processes, or the concept of processes. So let's think back for a moment to Java. In Java, we do things like define classes. A class is effectively a blueprint, right? It's a list of variables, it's a list of methods, how they're implemented. But by itself, a class doesn't do anything. It's just a blueprint for something that can be built. Later on in my program, I create objects. Objects are basically built from the blueprints of classes, where we've filled in the variables inside that class with actual information that is useful, right? So we've basically gone in there and populated in what are the variables inside of it, right? We've given it state. So the idea of a process is somehow similar to the idea of an object, in that it has basically been built from the blueprint of an executable file. So on your disk, right, when you go and you look at what you have available, right, you have these .exe files. These .exe files are basically the program code that lets you run a program. But until you double click on that file, nothing is happening. It's just there kind of waiting for you. It's basically a blueprint. Once you double click on it, it comes into memory, and all of a sudden it starts executing. It now has some state associated with it, right? The data that's holding on to. And maybe you do things, right? You give it orders to that program, and it'll go and it'll perform specific things, and maybe it computes some values. Basically what happens is it has some state that is now going to be alive, right? It's going to be changing over time. So basically, right, a process is to a class, excuse me, a process is to an executable what an object is to a class, right? It's an instantiation of that blueprint. Okay, so on the right-hand side, we have there basically a diagram to say, okay, how do these things look in memory? So a process, right, is a running executable, running program. It looks something like this. From the view of a process, basically it's inside of a virtualized environment. So it doesn't have to worry about the fact that there are other processes running on this computer. From its perspective, it's basically standing alone. What that means is that the memory locations that it's allowed to use basically can start at 0, right? So it's not off some random place in memory. It's actually just allowed to start at 0. So that's what we have here in our diagram, starting at 0. And I can go and just have whatever I want, right? So there are these 4 different regions here: stack, heap, data, text. But our process, right? Our process basically sees this micro world, if you would. It doesn't need to worry about anything else outside. It doesn't need to worry about, the resources are maybe having to be shared with somebody else, right? Somebody else is using the memory, next door. It doesn't worry about any of those things. From the view of the process, basically you have this virtualized environment. So what do these 4 different regions do? The stack is basically the stack, right? So when we do function calls within our program, we're going to do memory allocations there, right? And basically grow that forward. Right, so we push things on there, right? Function calls a function. We reserve memory in there. The other thing we have there next is the heap. So heap is going to be all the dynamic memory allocations. So usually I like drawing sort of a little cloud, right, with some blobs in there represent that I have different allocations of different sizes. Okay, so that's basically for our dynamic runtime allocations, right? Stack is for allocations based on functions that we can basically look at ahead of time and say, oh, hey, how much memory is this thing going to need? Here, basically, we're representing these both as stacks that go towards one another. For a heap, we don't really need to represent it as a stack. Here, they're just doing it because it's a diagram. Okay, then we have the 2 bottom regions there. So we have, of course, our data and our text. So data is hopefully what you're thinking, which is data is basically going to be a place to store information, right, to store data. So things in a C program like global values, right? So stuff that's stored maybe in static memory. So global variables, static variables, stuff that's going to be around for the duration of the program, right? For as long as that process is running. All that will be stored there in that little data region. Maybe things like constants as well, right? So maybe I have a long string, I have some localization stuff going on. I have this particular variable is set to this in English or this in another language. All those constants that are basically going to be unchanging will end up in that data region. Last thing I have there is a text region. Text region is just program code. So the actual program, right, that you're running will end up going down there, right? So all the functions and stuff will end up down there. Okay, so that's a general overview of what a process will contain in main memory, right? So I can picture, you have a process running now. So in general, there's some sort of tracking of what state that process is in. And down there at the bottom, I have kind of an abstract model of that. So there's 5 different overall states that a process could be in. Some operating systems have more, some operating systems have less. Usually, though, they kind of all will boil down to or reduce to this one diagram. So let's take a look at the steps in that diagram. What are the different states that my program could be in, right? When I say state here, really what I'm referring to is what does the process want to do, right? Not what information does it contain, right? No, what do the variables inside this process look like? But I'm literally saying, what is the process doing? Is it actively computing stuff, or is it just waiting for something, right? So kind of what part of the life cycle is that particular process in? All right, so looking down that diagram, we have 5 different options. First, we have kind of a new process. So that's a process that basically is being brought into main memory, right? So we're basically creating some storage for it, right, where we can place this image, where we can have a stack, a heap, a data, a text, where we can have all stuff, right? It's basically being brought into the scene for the first time, right? So it's a new process. So let's say you're done loading it, right, and you want to actually start running it, right? It's fully loaded. From there, right, you'll basically the state of it being admitted or being new, right, once it gets admitted, will become ready. So there's actually something called the ready queue, which is going to be effectively a list of all the processes that want CPU time. So a process that's in the ready state is a process that has work to do, right? It's ready to do computation, it's ready to run on the CPU. So let's say maybe it does run, right? It's on the CPU, you didn't have to wait any longer. Now you go to a running state. So the running state is just to represent, oh, hey, this process is actively doing computation on the CPU, right? So it's actually working. But at some point, usually the process gets basically pulled off because it needs to wait for something. It's no longer using the CPU. So maybe you do something like you say, okay, this process requests a file from my hard drive. Well, when it does that request, an I/O request, well, basically that request goes to the hard drive and sits in a buffer because there may be other requests pending. Obviously, right, there's some latency involved when we have I/O, right? We have to wait for our external device to get back to us. And so during that time, my program can't do anything. It can't do any other computation. It's just forced to wait for that I/O. Now, when that happens, what we want to do is we want to basically move to a waiting state where we're going to wait for the result from that I/O, right? We're going to just sit there and wait. So usually programs have this kind of, they have 2 parts related to them. They have what's called kind of CPU burst and I/O burst. So CPU burst is when the process just wants to sit on the CPU and does all its computation. Versus an I/O burst is when a program needs to do lots of I/O, right? So it makes a bunch of requests for files, and now it has to go wait while all those requests are resolved. So it'll kind of toggle between those 2 kind of characteristics, right? Requesting CPU time, requesting I/O time. But let's say you've requested I/O time, you're forced basically to be waiting around, and then once the device gets back to you, then you can go back to the ready stage, right? So you're able to do some computation again. Of course, right, you can't jump back to running because somebody will be doing their computation when that is, right? You can't just jump in there and preempt them. Really, right, once you get your I/O back, you still got to go back to the waiting queue, right, and wait for that. Wait for a CPU to become available again, right? And then you can go jump back to running and you can execute your stuff. Eventually, your program completes. So maybe the user tries to terminate it. Maybe the program just comes to the end and it needs to exit out. If that's the case, basically it'll jump to a terminated state, right? Where maybe the system is still temporarily hanging on to the information, right? So maybe some of the metadata associated with the process is still needed. Maybe this process has some sort of a child that needs the parent to stick around. But it'll sit there for a little while in basically a terminated state until it's finally flushed out of the system for good. So overall, right, this is basically how a process is represented, right, the different pieces of it that have to exist in memory, and then the different states that it can have. The next thing I want to talk about is executable formats. So how does a program look on the disk before it becomes a process, right? A process is a running thing, versus an executable is something that's stored on your hard drive. So whenever I have a program, basically it's going to have to adhere to some specific application binary interface, or some ABI. Basically what that is it's a specification of how this thing is built, how it's meant to run. So for example, what libraries was this built on, right? What system calls are going to be necessary? Also you have things like, for example, what architecture, right? Are you on a 32-bit, or is this a 32-bit executable or 64-bit executable? That will influence how memory is allocated for your process. All these things, right, kind of have to be specified somehow. So there are kind of 2 general formats. The first is ELF, the second is PE. So ELF is used on Linux, PE is used on Windows. So the ELF format is the one that's on top. So this is ELF. Initially, right, we have on the right-hand side, this is this is basically an exe file, right? I'm not gonna, I guess I can go and write, this is an exe. In Linux, right, typically won't be .exe, but just for the sake of annotation there. This is how the file is laid out. So we're not talking about memory, right? We're not talking about how this looks in memory, because that's basically what we already did in the previous slide, right? That was an image over here, right, of how that process looks when it's running in memory. This is how the process or the executable looks while it's sitting on the disk. So it looks a little bit different. So the first thing you'll have there is a header, right? And the header does things like specify the format, right? The ABI, right? What is it that the system needs in order to actually execute this file? What are the dependencies? That's followed by a little region here called program header table, which is basically going to describe how the file is broken down. So basically where are the different regions of either text data or data. The next couple of sections are going to look a little bit familiar, right? Inside the exe, you really have a text section. So that's actually going to be what's loaded into main system memory, right? All the constants, right? All the constants are there, all of the program codes associated with your program, right? All your functions, all your methods, right? All those are going to exist there as part of the text, right? That's stuff that basically we cannot alter. So it's all there in one block. Then it's followed in ELF format by RO data, which is something we didn't have in the previous slide. But RO data is basically just read-only data. So that's things like constants, right? So things that have a static memory allocation, but which are also constants, will go here in RO data. Sometimes there can be multiple chunks here. So sometimes there's RO data 1, 2, 3, whatever. I can have different chunks of data, right? Or maybe even different types of data. And then of course then, right, I have just data, which is going to be where I can put all my static variables in, right, or global variables in there, right, the stuff that's going to persist for all of time. It's basically going to have the information of, okay, I have these variables that'll need to be stored. And then at the end, there's basically another table to basically describe the contents of what's in here again. Remember that when you're loading these things, basically you just have a wall of ones and zeros, and you basically need to have some way to indicate, oh, hey, this is where this information starts versus where this information starts, where this information starts. So that's the idea behind ELF. So it's pretty closely ties to what we talked about on the previous slide, but now we have some RO data as well. On the flip side, we have Windows, right? So Windows has the PE format, and this is actually the Win32 format. So the problem with PE is it's a very old format. They've been using it since DOS, right? So they've been using it for multiple decades. This kind of shows up instantly, and if you look at a PE format file, there are 2 headers on it. In terms of ELF, we just had one header that laid out, that said things like, okay, this is the architecture I expect, this is the format that I'm using. Over here in a PE file, that's not the case. And so this is also literally a .exe file on your system. So this is .exe. Go here, .exe. You'll notice that in the diagram on the right-hand side, the first thing it says is DOS header. So actually, there's kind of a dummy header on your file. So even though I could have a file, a .exe that I run on my Windows 10 machine, it'll have in there a header just for DOS. So that even if I somehow end up on a 16-bit DOS system, I can still type in the name of the file, try to run it, and get back an answer. Usually what happens is that little header there, that DOS header, will basically redirect me to some little program code that says, this executable will not run on 16-bit DOS, right? So that's the entire kind of program that would run. So it's almost as if, right, there are 2 programs in your exe. One which is the actual one that you intended to use, and then the other one is just kind of a stub to say, okay, if you run me on a DOS system, I will give you an error message. So there's really 2 programs in one. So that's kind of just a legacy thing because basically based on the requirements for this file type, it should be something that we can run anywhere. So let's say you're on a more modern system. A more modern system will actually skip over the DOS header and jump to the main PE header, which is much more modern and contains the same information as the header in the ELF file, right? So it's going to specify things like the architecture or what libraries are required. So that's pretty much a matchup there. There's some optional information. We don't need to really worry about that stuff here. And then we have basically some annotations about where things are stored, right? So where is data stored, right? So data, of course, is being the global variables, right? The stuff that has static allocations. Where is that coming from, or what do I need there? More kind of annotations, how are things broken up? And then we get right over to our code, right? And so code is basically taking the place of text. So that's, again, going to be our program code. What exactly is it, right? The line by line of how do we execute something, right? How is this particular function, built? All of the code for that is stored in the code section. Then lastly, right, we have some information about imports, right? So maybe what DLLs do I need? We'll talk about DLLs later. And then, finally our data section, right? Where basically these are the global variables or the static variables, right? The static memory stuff that you'll need to use, right, during the run of this program. So that's the layout for a Windows file. There's basically a header followed by a bunch of information that is associated with it. Okay, so moving forward, the next thing I want to talk about is our process control blocks. So remember way back on the first slide, we said the processes basically have this virtualized view. So they are the only thing that's running on this system, right? Or the only thing running on the CPU. How can we support that? Well, we support that with something called a process control block. A process control block is basically a data structure that's in charge of keeping track of the state of an entire process. So there are a ton of things in there. For example, program state, program counter, CPU register, CPU schedule information, memory management, accounting, all these things, right, are all in this process control block. Ultimately, it's this data structure. And the idea is that I'm going to store my process in these control blocks so that I have a way basically to remove them from the CPU, right? So something is running, right? A process is running, all of a sudden something else needs to run, right? Something preempts it. Or maybe, the first process is doing some I/O and it doesn't have anything to do and it just needs to wait for a little bit. That means we need to pull it off the CPU. So we pull it off the CPU and put something else on there. And the way we kind of represent our processes frozen in time, if you would, right, is with a control block, right? A process control block or a PCB. So PCB stores all this information about a process. It's basically just freeze it in place so that we can take it off the CPU and put something else on there. And later on, maybe we want to put that process back so we can restore the state of the system from that process block and get it running again. So let's take a look at this picture for a second here. So this picture on the right, on the left-hand side, has basically two processes. It's for a system that has only one CPU though. Time starts at the top of this graph. So over here, basically time begins. And let's say, right, that our initial process is running, right, before this point, right, our first process 0 is running. And then all of a sudden, maybe it does some I/O and has to take a break. What happens is that there is basically an interruption, right? We freeze that process and save it into a PCB, into a PCB data structure, right? So this stuff here will save out process 0. So now my CPU is empty. What I need to do is basically start a new process. So I load state from another PCB. So this is the PCB for process 1, right? This is going to be a second process that's running. So we load that, right? That was something that was saved out to main memory, and then we spend some time executing that. That's process 1. Maybe process 1 hits some I/O, it finishes, or it's waiting for something else. Then we need to basically save its state from the CPU back into that PCB, right? PCB1. Okay, now the CPU is idle again, and so now we can think about maybe restoring the first process. So maybe its I/O is completed and it's ready to go again, and so we can reload the state from PCB0, right, that we saved earlier, reload that over here, right, and get that process running again so it can do other stuff in the future. Meanwhile, process 1 basically had an opportunity to run for a little bit, right, over here, and then now over here, right, it's basically back to not doing anything, right? Saved to a PCB, it's waiting to get more time. So that's overall kind of flow control here, right? We have processes, they run for a little bit, save them, load something else, it finishes, reload the other one, well, save the second one, reload the first one, continue with the first one. So this is the basic process that's supported by these process control blocks. Okay, so let's just take a brief look at how process control blocks are represented in the Linux kernel. So this is something called struct task struct. So a task struct is a PCB, so it's used to represent basically the entire state of a running process on Linux. So I have, and they call this a process descriptor, is the official term. The actual data structure itself is just called task struct, and it's a struct, of course. On the right-hand side, I have the source code for this. So this is actually pretty long. If you go and you look in basically the Linux kernel files, there's a ton of stuff in there. This is actually from line 1475, so there's a ton of stuff in this scheduler.h file. It's in a file about the scheduler, so I didn't really talk about this, but it's actually going to be kind of a bit of an issue, right, for us basically to pick what processes run when. We'll actually devote an entire kind of unit of content to that, basically this idea of how do I do CPU scheduling. But that's a little ways out. So anyways, this is a struct that stores all the information about a running process. I've actually omitted some stuff here. I've omitted about 400 lines of basically some boilerplate stuff, some preprocessor stuff. So you can see there's a lot of things in there, right? We're storing things like, for example, what is the state of my program? Process, which is actually a little bit more general than the state we introduced last time. We have things like a pointer basically to reference what is on the stack. There's maybe different flags about what is happening in our program. There's some priorities associated with it, right? These are maybe having to do with scheduling stuff. Scheduling stuff, I'm trying to highlight this here. Stuff about security, more stuff about states, stuff about maybe unique identifiers, how it relates to other processes in the system, all this kind of information. It just goes on and on. Right, so there's this massive struct, right, task struct, and basically that whole thing, right, the stuff we're looking at is all the information we need to collect if we want to keep track of a process running in our system. So we want to pull it out from the CPU. We need to save all this stuff. We want to restore it to the CPU. We need to restore all this stuff. So this is basically a process, right, frozen in time is what we're looking at on the right-hand side. What is all the data that I need there? So in Linux, they store these actually in a doubly linked circular list. The idea being, right, is it has to be doubly linked because, well, hey, I'm going to both add processes and remove them. Generally speaking, removing processes is something that's much easier to do with a doubly linked list because you have kind of a backward reference to repair basically the place you're coming from. It's circular just so that we can basically iterate through it easier. Bottom left, last thing I want to mention here briefly, these are the states in Linux. So before we had to introduce 5 different states. Basically a new process, a ready process, a running process, a waiting process, a terminated process. That's what we had introduced before. Here this thing is a little bit different. There's still 5 states in Linux, but basically they have different names. And the middle 2 are kind of combined, right? So task running, right? So task running is basically the analogous to it being either ready or running in our general diagram of the states that a process could have. But basically, right, Linux groups them together and just says task is running, right? And then on top of that, and then in addition to that, there's a little flag that basically says, okay, you're running. Are you active, or are you waiting to get CPU time? So there's kind of a flag on top of that, although there's only one overall state. The interruptible and uninterruptible, this is basically just our waiting state, right? So Linux kind of also makes this distinction of, oh, hey, some things, maybe I do want to notify them if something happens, right? So you can maybe imagine a process is running, it makes an IO request, it has to wait for something to hear back from it, so it goes and starts to wait around. And then there's processes, right, that maybe I can interrupt them, right? Even if they're waiting for something, I can interrupt them. Or maybe there's other processes that I don't want to interrupt because maybe the resource they're accessing is very fragile, I don't want to disturb anything. Linux will actually tag that, right? So it'll say, is this task something I can interrupt or I can't? The last difference is the top right in that diagram, where you can see basically we have a task zombie. So that's for a task basically they have been orphaned. There's no way basically to clean up after them. We call them a zombie process, right? It's a process basically stuck running and nobody really knows what to do with it. We'll actually go into more detail on that later, but for now, just kind of know that that's what it's called in Linux. So if you ever do something like a top command, you may see how many zombie processes are sticking around your system. All right, so last thing I want to just mention briefly is memory allocation for this thing called task struct. So task struct, one of the issues with it basically is that this process control block, these things come and go all the time, right? We create new programs all the time, we destroy programs all the time. And this is a little bit problematic because it takes a lot of time basically to do memory allocations for that struct, right? That struct is a data structure that I need in memory. But doing something like a malloc or a free, that's rather expensive because I need to go and talk to basically the entire memory allocation subsystem to figure out where it is that I can place this, right? Where are the different pieces of memory that I can use? That's a little bit just slow. So one thing they usually do is they have this idea of maybe I have some task structs that are live, right? Things that are running in my system. So let's call these, just draw a few boxes here, and let's say these are task structs active. Right, so these are things that are running. And then also what a system will actually do in order to basically speed up the malloc and the freeze is we'll have something called, let's call this a task struct pool. So this is actually going to be basically a list of all the task structs that have been allocated but that aren't currently in use. So let's say in our picture, right, our picture says that there are basically four running processes. So say process 1, process 2, process 3, process 4. Those things are all running. And then in my task struct pool, right, this is a memory pool. This is what we call pooled memory allocation. There may be a couple of task structs that are basically blank, that nobody's using them, right? So these are things that I malloced earlier in my my run, right? My operating system has been around for a while. I had some more processes earlier in the day. And so instead of basically freeing the memory for that task struct when those processes are completed, I just basically tuck them away, right? So I put them in this pool. And so I still have the memory allocation devoted to me. So what I could think about doing is, okay, maybe process 5, I need to run process 5. So what I can think about is, oh, hey, process 5 comes along, so I can basically take an element out of this task struct pool and put it over here. And in there I can store number 5. So I can basically avoid having to do my malloc because I'm just going to reuse the memory allocation that I used earlier in this program, in this operating system's execution, right? So earlier in the day. Or maybe, I over here on the flip side, right, maybe I'm done with process 4. Instead of doing free on that task struct, I would basically just X out here so it's no longer used and add basically another element to the free pool. And that's something I can use in the future. So this is just kind of a general idea, right? This is pooled memory allocation. The idea is we want to avoid mallocs, we want to avoid frees. And when we do that, we'll basically just maintain a list on the other side of what are the kind of the allocations I already have available to me so I can reuse them if I want to. So just keep that in mind. That's how this stuff is implemented on the backside. Later on, we'll get to memory management in this class, and we'll talk a lot more about basically how we can handle things like this, right? Basically ways to speed stuff up.